Space telescopes have revolutionized our understanding of the universe by observing celestial phenomena from beyond Earth's atmosphere. Unlike ground-based telescopes, these instruments avoid atmospheric distortion and light pollution, enabling unprecedented clarity and sensitivity. This essay explores the fundamental principles, technological innovations, and operational challenges of space telescopes, focusing on iconic examples like the Hubble Space Telescope and the James Webb Space Telescope. By examining their designs, capabilities, and scientific contributions, we illuminate how these engineering marvels function as humanity's eyes in the cosmos. At their core, all telescopes operate on the principle of collecting and focusing electromagnetic radiation to form detectable images. The effectiveness of a telescope depends on its aperture, the diameter of its primary light-gathering component, which determines both light-collecting capacity and angular resolution. Larger apertures capture more photons, revealing fainter objects, while minimizing diffraction effects to sharpen images. For space telescopes, this capability is enhanced by their position above Earth's atmosphere, which absorbs or distorts certain wavelengths like infrared and ultraviolet. Space telescopes often employ reflecting designs using curved mirrors instead of lenses. Mirrors avoid chromatic aberration inherent in lenses and are structurally easier to support in large apertures. The Hubble Space Telescope, for instance, uses a 2.4-meter primary mirror to collect visible, ultraviolet, and near-infrared light, while the James Webb Space Telescope's 6.5-meter segmented mirror specializes in infrared observations. By focusing light onto detectors such as charge-coupled devices, these telescopes convert photons into electronic signals, which are transmitted to Earth for analysis. Most space telescopes, including Hubble and James Webb, utilize reflecting telescope designs. Isaac Newton's innovation of using a parabolic primary mirror to focus light revolutionized astronomy by eliminating chromatic aberration and enabling larger apertures. In space, mirrors are preferable due to their lightweight construction and durability under extreme thermal conditions. James Webb's primary mirror, composed of 18 hexagonal beryllium segments coated with gold, exemplifies advancements in material science, optimizing both reflectivity in infrared and thermal stability. James Webb's design addresses the unique challenges of infrared astronomy. Since infrared radiation is emitted as heat, the telescope must operate at cryogenic temperatures to avoid self-interference. Its 5-layer sunshield, the size of a tennis court, blocks solar heat and light, allowing the instruments to detect faint thermal signals from the early universe. Unlike Hubble, which observes primarily in visible and ultraviolet spectra, James Webb's infrared capabilities enable it to peer through cosmic dust clouds and capture light from the first galaxies formed after the Big Bang. Earth's atmosphere absorbs much of the electromagnetic spectrum, particularly infrared, ultraviolet, and X-rays. Space telescopes circumvent this limitation, offering unobstructed views. For example, James Webb's location at the Sun-Earth L2 Lagrange point, 1.5 million kilometers from Earth, provides a stable thermal environment and minimal light interference. Additionally, the absence of atmospheric turbulence allows space telescopes to achieve diffraction-limited resolution, where image sharpness is determined solely by aperture size and wavelength. Precise pointing is critical for long-exposure observations. Space telescopes use gyroscopes and reaction wheels to maintain orientation. Hubble's recent gyroscope issues highlight the importance of redundancy. In 2024, a faulty gyro prompted a switch to single gyro mode, reducing observational flexibility, but extending operations into the 2030s. James Webb employs micro-shutters and fine guidance sensors to align its mirrors with nanometer precision, ensuring stable imaging over hours-long exposures. Launched in 1990, HST has provided unparalleled views of the universe across ultraviolet, visible, and near-infrared spectra. Its corrective optics mission in 1993 resolved initial mirror flaws, showcasing the potential of in-space servicing. Hubble's contributions include determining the rate of universal expansion, capturing detailed images of planetary nebulae, and observing exoplanet atmospheres. Despite aging hardware, NASA projects Hubble's operational lifespan into the 2030s, aided by adaptive control modes. JWST, operational since 2022, represents a quantum leap in infrared sensitivity. Its 6.5-meter aperture and suite of instruments, NIRCam, MIRI, and NAIR-SPEC, enable spectroscopy of exoplanet atmospheres and imaging of galaxies at redshift Z20. The telescope's deep field image, capturing thousands of galaxies in a grain of sand-sized sky area, illustrates its power to probe the cosmic dawn. JWST's design incorporates lessons from Hubble, including modular components for potential robotic servicing missions. Emerging designs, such as the proposed 6-meter on-axis space telescope, prioritize cost efficiency and manufacturability. Using a 3-mirror anastigmat (TMA) configuration, this concept achieves diffraction-limited performance with simpler alignment and reduced stray light, leveraging materials like silicon carbide for lightweight, thermally stable mirrors. Such innovations could democratize access to space-based astronomy. Space telescopes face challenges like orbital decay and component degradation. While Hubble's orbit decay is projected to occur post-2035, proposals for commercial reboost missions using SpaceX Crew Dragon were deemed premature in 2024. Future missions may incorporate autonomous docking systems or in-orbit manufacturing to extend lifespans. Space telescopes like Hubble and JWST exemplify humanity's quest to explore the cosmos unfettered by Earth's limitations. Through innovative optical designs, advanced stabilization systems, and strategic orbital placements, these instruments transcend atmospheric interference, capturing data that reshapes our cosmic understanding. As technology evolves, next-generation telescopes will further enhance our vision, probing darker corners of the universe and unraveling mysteries from dark matter to extraterrestrial life. The legacy of space telescopes underscores the synergy between engineering ingenuity and scientific curiosity, driving humanity's timeless journey to comprehend the stars.